Welcome everyone. This is a video dealing with 9.3, which is graphing rational functions. We want to start off with noticing all the things that we need to kind of look for before we can start graphing. So the first of which is to find any of the holes that we might find in our graph. Holes will come from any canceled factors, where we cancel in the numerator and the denominator. And remember, these factors have to include x. Then we'll look for vertical asymptotes, which are zeros of the denominator. So we take whatever factors we have in the denominator that have x in them and set them equal to 0 and solve. And remember, you can associate vertical asymptotes with the idea that a vertical line is undefined, and to have a 0 in the bottom of a fraction makes the fraction undefined. So try and marry those two ideas together. Then we look for any horizontal asymptotes. And remember, for those, we look at the degree of the numerator versus the degree of the denominator. If the degree of the numerator is less than the denominator, then we get a horizontal asymptote of y equals 0. If the degrees are equal, we get one where y is equal to the leading coefficient of the numerator divided by the leading coefficient of the denominator. And if the degree of the numerator is greater than that of the denominator, then we don't have a horizontal asymptote. Although there is something else that we can figure out about the graph, knowing that. And finally, the last two things I'm having you look for are x-intercepts and y-intercepts. To be an x-intercept, the y value has to be equal to 0. Because we're dealing with fractions, a fraction that has a 0 in the numerator makes the whole fraction equal to 0. So we just look for any zeros of the numerator for our x-intercepts. For our y-intercepts, we're going to go through, set all of our x's to 0, and we're going to solve for y, and that's going to give us our y-intercept. All right, so now that we have the 5 things that we're looking for, let's go and take a look at this first equation. So we have y equals 3x squared plus 6x over x squared plus 6x plus 8. So before we can really do anything, we really have to factor this, because we have to know if there's anything we can cancel. So we have to know if we can cancel any factors. So starting off at the top, we have this 3x squared plus 6x. So remember, we look for anything that we can pull out. Well, they both have a 3 in common, and they both have an x in common. So let's pull a 3x out. So we have 3x, and then what's left behind is x plus 2. So that's our numerator, and let's do the same thing to the denominator. So we don't have something we can pull out, so we just look for the factors of 8 that add up to 6. So those factors might be 4 and 2. So x plus 4, x plus 2. And remember, they're both positive, plus 4 and plus 2, because the 8 is positive, so your c term is positive. That means they're both going to be the same, and you go and check out the b term, and that's positive 6x, so we know they're both going to be positive. Okay, so now that's what we're going to consider when we think about this equation now. This is factored form. So let's move back over to holes and see if we can't come up with any holes in this graph. So you're going to rewrite your function, and I'm going to ignore the y for right now, just because we're only going to look for ones we can cancel that have to deal with x. So we have our 3x times the x plus 2 over the x plus 4, x plus 2. So quite obviously, there is something we can cancel. We can cancel out the x plus 2's. All right, the canceled factors, remember, we have to set equal to 0 and solve. So if we do that, we have x plus 2 equals 0, which means that x equals negative 2. So we're going to have a point on our graph that's negative 2 comma undefined. That's going to end up being a point on our graph. So it's something to keep in mind. But lucky for us, now that we've canceled out those factors, the x plus 2's, our new function that we have to deal with is really just the 3x over the x plus 4. It's kind of nice. It makes our lives just a little bit easier. All right. So let's move down to finding vertical asymptotes. And remember, we just have to use the 3x over the x plus 4. So we're going to take our denominator, the denominator being that x plus 4, and we are going to set that one equal to 0. So we have x plus 4 equals 0, so x equals negative 4. Now, the vertical asymptote is a line, and that's the equation of a line, x equals negative 4. Perfectly rational, or a perfect example of a line. Okay, we've got that one down. So let's move on to horizontal asymptotes. So horizontal asymptotes tell us that we want to look for the degree of the numerator versus the degree of the denominator. And remember, again, we only have to care about what's left over. So the 3x and the x plus 4. So the degree on the top is 1, and the degree on the bottom is also 1. Because it's x to the first on the top and x to the first on the bottom. So 1 is equal to itself. So we are going to find a horizontal asymptote when we take the leading coefficient of the numerator and divide it by the leading coefficient of the denominator. So in our case, that means we're going to get y equals the leading coefficient of the top, which is 3, over the leading coefficient of the bottom, which is 1, or more simply, y equals 3. Excellent. All right. Now to finish this off, so we're just going to see if we have any x-intercepts, and any y-intercepts. These are by far the least important of all the information that we had to pull out of this graph. But they work as points. They kind of help give a shape to the graph. They're points that you could talk about and other people could identify very easily on your graph, so they're worth looking for. All right, so x-intercepts are the 0 of the numerator. So we just take the numerator, 3x, and we set it equal to 0. Well, we can divide both sides by 3, and we get x equals 0, which means we get the point 0, 0, because x-intercepts always have a y value that's equal to 0, and we found the x value was also equal to 0. Ooh, that erased quite a bit more than I was anticipating. Let's bring that down a little bit. All right. So we don't have to look for a y-intercept now, because if we find that the x-intercept is going to be 0, 0, then that's already your y-intercept. So there really isn't anything else to find. Although if we've plugged it in, we would get exactly the same answer. All right, so now we have everything that we need to at least get to our x and y chart. An x and y chart, you get to pick any value of x that you want, but because we have a vertical asymptote, that helps us. That says to us, okay, well, the vertical asymptote is sort of like a dividing line for us. So we kind of think about our x and y chart as being above and below the vertical asymptote. So if I'm going to pick points, I would say let's do 2 that are less than -4 and 2 that are greater than -4. So less than -4 might be -5 and maybe -6, and greater than -4 maybe -3, but I would also choose 0 because we already know the point. 0 is going to come out to be 0. It's going to be 0, 0, because that was our x and y intercepts. So I would definitely use those points. Be careful that you don't use -2, because -2 we already found was going to be undefined. So you don't want to use that one. Okay, so to find our y values that go with these x values, we're just going to plug in. And again, which is kind of nice here, you can plug into the simplified version. So we can plug into 3x over x plus 4. All right, so let's do that. So our first one will be -6, and I'm going to do it right here under the original equation. So we're going to have 3 times -6 over -6 plus 4. All right, well, 3 times -6 is -18, and -6 plus 4 is -2. Negative divided by negative is a positive, and 18 divided by 2 is 9. So 9 is a point on our graph. So -6, 9. All right, we're going to repeat this process, and we're going to do that next with -5. All right, so we're going to fill in 5. Okay, well, 3 times -5 is -15, and -5 plus 4 is -1, which gives us just +15. Excellent. So now negative 5, 15 is a point on our graph. And just one more, just plugging in negative 3 this time. So get rid of these guys right here. And remember, you don't have to erase. I'm doing it simply for the sake of space on the screen. So you've got negative 3 in both those places. So 3 times negative 3 is negative 9. And negative 3 plus 4 is 1. So we are actually going to get a negative number out of this one. So negative 9. Okay. We've got everything now that we could possibly need to graph this. So the first thing you want to do is put on your asymptotes. So if x is negative 4, we go to on the x-axis to where x is negative 4, and we draw a vertical line, a line that goes up and down from that spot. Because anywhere on this line, x is equal to negative 4. We do the same thing at y equals 3. So we go on the y-axis up by 3, and we draw a vertical line. Oops, try and get that to actually start in the right spot. Sort of. Imagine it was exactly at 3. So we have our two asymptotes. And when we have a graph like this, you're going to expect that you're going to have graph either in the upper right-hand corner and lower left-hand corner, or vice versa. Because it looks like this is going to be one of those more simple rational functions. It's just the only difference is it's going to have a hole in it. So we're going to plot our points. 15 and 9 are going to be a little bit hard to show. So we might want to go and count by something a little different, or just to say, well, 15 is going to be the highest point on my graph and 9 is going to be a little less than that. Just because there's always going to be points that are off the graph. It's sort of how it works. So if that's going to happen, because our graph is only going up to, say, 7, 8, 9 or so, let's say the top number is going to be 15. And if you label this, then I would have no problem at all. So let's just say this is going to be 15, and maybe a little ways down from that would be 9. Okay? Because we're just getting an idea of what this graph looks like. We don't have infinite graph paper. If you want to count up 15, sure, that's absolutely fine. You would never lose points for doing something slightly more accurate than I can quite get on the computer. All right, so erase this guy, and let's plot our points. So we go down to where we're at negative 6, and then up to the 9, and put a point. Ooh, and it's having a little trouble doing the points. Give me just a moment. So I get that on there. Okay. So negative 6, and where we put the 9. Okay, you have that point. And then negative 5 and 15. Excuse me. All right, negative 5 and 15. There we go. All right. So we want to use our asymptotes to help us graph from this point. And I'm only putting 2 points on because I really want to drive home the idea that we're only going to be connecting these 2 points together. They're not going to be connected to others. All right. So this is a bit tricky, but remember, you're going to try and make a curved shape that gets closer and closer to the asymptote, but never crosses it and never touches it. Okay, so that's pretty good. It's getting closer to our asymptotes. We're a little far away. That's okay. That happens to be the points that we chose. Good. So now let's go and draw the one on the other side. So we have the point 0, 0, which is nice. It's always great to have that point. And we also have the point negative 3, negative 9. Now, of course, negative 9 is not going to fit on the graph either, so I'm going to go to about here and call that negative 9. All right, and we're going to put that point on, so 3 down, and where are we putting the negative 9? Excellent. Okay, now I want you to again connect those 2 points trying to use the asymptote as your guide. So it's getting closer to it, but not going to cross it. Very nice. All right, and we're going to do, this is almost perfect because it looks like that simple rational function, but we have to go back to the fact that first thing we found was that there was going to be a hole at negative 2. All right, so what you're going to do is you're going to come with your eraser, and you're going to go to where x is negative 2, and then you're going to go until you find graph. So right here where I'm erasing is where x is equal to negative 2. So this one spot in our graph, there's actually a hole. One little place where it's undefined, so we can't put any, either one of our branches of this hyperbola can't go in that particular spot. It's not as dire as, say, a vertical asymptote that we can't cross, but it does just leave a hole in the graph. Excellent. So right here you have it. This is y equals 3x squared plus 6x over x squared plus 6x plus 8. Very nice job. All right, let's take a look at this one. This is a different rational function. This one is negative 4 over x squared minus 5x plus 4. So we're going to do the same thing to start us off again, which is to factor it. Because again, we really can't do anything until we figure out if there are any holes, and to do that we need to know if it factors. Although taking a look at the top has no x's in it, so that's good. We know there aren't going to be holes, but let's still factor it just so to make things a little bit easier. Okay, factors of 4 are going to be 4 and 1, that add up to 5, and of course, because the 4 is positive, they're both going to be the same sign, but because the 5 is negative, they're both going to be negative. All right. Oops. So we can scooch over to holes, but because we know that you only have this 4 on the top and the x minus 1, x minus 4 on the bottom, nothing can cancel. So if nothing can cancel, there are no holes. So no holes. All right. Then we jump to our vertical asymptotes. And vertical asymptotes, remember, are those zeros of the denominator. So we take the 2 in the denominator, our x minus 1, we set it equal to 0, and our x minus 4. Well, we're going to solve for both, so we get that x equals 1 and x equals 4. That means we have 2 vertical asymptotes this time around, which is kind of nice. It means we have to look for a few extra points, but it presents a really interesting graph, so it's kind of fun. All right, jumping down to our horizontal asymptote, remember we've got negative 4 over this x plus, x minus 1, x minus 4. And what you want to think about again is the degree. So if we look in the numerator, there is no x value. We could put an x value in as long as we made it x to the 0. Okay? So the degree of the numerator is going to be 0. And the degree of the denominator, remember that's the one we started with before we factored it, because we have those 2 x's, is going to be x squared, which makes the degree 2. Okay, so 2, being the denominator, is greater than 0. 2 is greater than 0. So in that case, the degree of the denominator is going to pull our fraction ever closer to being 0, but it's never going to allow it to be. So our horizontal asymptote will be y equals 0. This will happen every time the degree of the denominator is greater than that of the numerator. All right, let's jump down to our x-intercepts. So we want to take a look. That would be the zeros of the numerator. Our numerator is just negative 4. Because there are no x's, there can be no x-intercepts, so there are none. And that makes sense because we just said y equals 0 is an asymptote. It doesn't always mean that we won't have an x-intercept because there are occasional times when you do cross the horizontal asymptote, but in this case, there are none. Okay, and it makes sense. All right, then we check for y-intercepts. Oh, apparently my little y didn't transfer over. Put my y in. Okay, and that's when we set our x's to 0 to solve. All right, so we go to this guy and we go, all right, well, we got y equals negative 4 over 0 minus 1, right, because that's an x to 0, and 0 minus 4. Okay, so on the top we still have negative 4, and on the bottom we have negative 1 times negative 4, which is positive 4, so we get negative 1. So we're going to have a y-intercept And remember, y-intercept means your x value is 0, at 0, -1. So we do have a y-intercept. That can go right into our x and y chart or right onto our graph, either way. Okay, so now that we've come up with all of those 5 things, we want to jump back up to our x and y chart. And you want to remember that we have to pick points around our vertical asymptotes. So because we have the one that's x is 1, I want you to think about that being a dividing line. And I want you to think about the same thing with x is 4. So we're going to pick 2 values that are less than 1, 2 values that are between 1 and 4, 3 values that are between 1 and 4, and 2 values that are greater than 4. So we can pick some pretty easy ones. We can pick 0. 0 is an excellent one, plus we already know it's going to come out to be -1. And maybe -1 might be the other one we pick. Between 1 and 4, we might pick 2, or maybe even something that gets us really close to 1 but isn't 1. Maybe 1.5, maybe 3, and maybe 2, and maybe 3.5. So we get really close to those asymptotes. Do you have to pick decimals? No, but you do have to pick 3 numbers in between, which in this case, because it's only between 1 and 4, only leaves you with picking at least one as a decimal. But you could do 2 and 3 and 2.5. Those would be excellent points as well. But we also need 2 greater than 4, so maybe 5 and 6. Excellent. All right, we're going to plug those in. Switch back to black. All right. So I'm going to go right here under, you can do it in your original or you can do it in your factored form, whichever you find easier. I'm going to do it in the factored form. So we've got y equals -4 over -1 minus 1 times -1 minus 4. So that one's going to be -4 over -2 and -5 multiplied together, and that's 10. So we have -4 tenths or -2 fifths if you prefer. Okay, putting that point in. Okay, I'm going to do it again, this time using the next set of numbers. Okay, we can skip 0 because we already know what that one's going to be. So we're going to have, let's see, what's the next one? 1.5. So we're going to have 1.5 minus 1. And we're going to have 1.5 minus 4. So on the top again, we get that -4. On the bottom, this guy is 0.5 positively. The next one is, let's see, -2.5, if I'm not mistaken. Yep. All right. So half of 2.5 would be 1.25, and that'll be negative. So it'll be -1.25. Okay, so the 2 negative signs are going to cancel, which is nice for us. So we're going to get a positive out of it. And it looks like we have to try and figure out how many times 4 goes into 1.25. And at this point, you certainly can switch and actually do this division. So let's do 4 divided by 1.25. And you can do it with your calculator. And we get 3.2. And so that's what we're going to put in to our X and Y chart, 3.2. Because remember, I have no problem with you using decimals to graph. It's a little bit easier. Okay. So again, erasing these. And we're going to fill in our next number, which happens to be 2. So we're going to have 2 minus 1 and 2 minus 4. That gets us -4 over 1 times -2, so over -2. The negatives again cancel out, and 4 divided by 2 is 2. So that's kind of nice. Nice work that kind of worked out that way. Ooh, sorry, that did not erase. There we go. And last one in the middle, we're going to pop in 3.5. So we're going to have 3.5 minus 1 and 3.5 minus 4. All right. 3.5 minus 1 is 2.5. And 3.5 minus 4 is -0.5. So if we have 2.5 times a -0.5, we have, again, -1.25. And so this is going to be negative 4 over negative 1.25, which we already saw was 3.2. Very nice. All right, last two. And these should provide us with a little bit easier math because they're going to be integers. So we have 5 and 6. So we're going to do 5 minus 1 and 5 minus 4. All right, minus 1 is going to get us 4, and 5 minus 4 is going to get us 1. So we have negative 4 divided by 4, which is negative 1. Okay, repeat the process with 6's. We get 6 minus 1, and we have 6 minus 4. So 6 minus 1 is 5. 6 minus 4 is 2. So we're going to get negative 4 over 10, which is negative 2/5. It's kind of nice how symmetric this graph has really turned out to be. Okay, so we've got our x and y chart. We've got all this information about holes, asymptotes, and x and y intercepts. We're going to put on our asymptotes now to get us started. So we have 1 at x equals 1, so that's right here, and 1 at x equals 4, and that's right here. Okay, we also have a vertical asymptote at y equals 0, so we're going to put that in as well, and that is our x-axis. So I've put it on top, but it's just a reminder that we will likely not cross this area. All right, let's now just put our points on, and again I would do that in the sets that we've done them. So put the 2 on that are less than 1, then put and draw that part of the graph in. Put the 3 on that are between 1 and 4, then draw that part of the graph in, and put the 5 and 6 on and draw that part of the graph, because these aren't going to connect because of our vertical asymptotes. So starting at negative 1, we have negative 2/5, which is a little less than negative 1, a little more, a little farther than 0, but a little not quite as far as negative 1. That's how we want to think about it. So negative 1 and a little bit. And again, you're not a computer program. I don't expect you to get that exact. I'm not going to come by with a ruler and say that's not 2/5. And of course 0 and negative 1 as well. All right, we're going to plug that in. And again, use those asymptotes to help you graph the rest of it. Oop, my arrow looks like it's crossing, and I don't want you to think that it is. It's not like that. Very nice. Okay. Use the asymptotes to guide you. So we have the 2, the red one that's horizontal, y equals 0, and the vertical, x equals 1. All right, now putting the points on in the middle, I get 1.5 and 3.2. 1.5 is about half, and 3.2 is just a little bit more than 3, so it looks like somewhere in there. Between 3 and 4 is perfectly fine. And the same thing with the 3.5. Oh, it seems a little bit high to me, so I'm trying to make it a little more symmetric. Good. And at 2 and 2. Looks like a point. So they don't exactly show you what the graph's going to look like, but because you have at 1.5 and 3.5, they're at the same spot, the graph has to turn around at some point. So again, use these as a guide. So I'm probably going up and through these points, some point turning around and coming back down like that. And that's perfect. Okay. You kind of have to go with your gut on some of these. Some of them don't exactly show you what it's going to look like, but you have to kind of give it your best shot. So we have another point here at positive 5 and negative 1, and another at 6 and negative 2.5, which again is more than, a little farther than 0, but not quite as far as negative 1. A little bit of trouble getting this point on where I would like it. There we go. All right, use those asymptotes again to help guide you. And there you have it. Now we've graphed ones like this before in class, but if you notice, it's almost upside down to ones that we've normally graphed. Normally we see these two branches of the hyperbola in the upper corners, right and left, and we normally see the parabola-like shape in the middle, but going down. So the reason this is sort of flipped from what we're used to is this negative sign all the way in front of our equation, this guy right here. and I'll highlight it in case you missed that. It's this negative sign right there, right here. So that guy is really what made the whole graph flip upside down. Well, this is one that you could expect to see on a test or a quiz, and we were able to graph it just knowing our vertical asymptotes and using all the information that we normally find and doing an X and Y chart. So very good. Excellent. Let's try and do just one more example. All right, here is the last example. So if you take a look at this one, again, we would always go after trying to figure out our wholes first, which means we have to try and factor. But on the top, there's nothing to factor. It's already in the factored form. It's 5 times x. On the bottom, we have x squared plus 1. If you remember, there's no such thing as a sum of squares. So x squared plus 1 cannot be factored. Well, hey, if it can't be factored, then we know something already. We know that there are no wholes because there's no way we can cancel anything out. So no factors, no wholes. All right, one thing down. All right, vertical asymptotes. Vertical asymptotes are found by setting the factors of the denominator equal to 0. Well, we can't factor it. It's x squared plus 1. So even if we try, we're going to get x squared equals negative 1. And our next step would be to take the square root of both sides. But we know the square root of negative 1 is I. Now, finding the zeros of the denominator are only for real numbers. So there are no real numbers, no real zeros. So there are no VAs, no vertical asymptotes. So we got no VA. We have so far no wholes. It's not giving us a ton to go on because actually having this information gives us sort of a place to start our graph. Well, at least we can still look for our horizontal ones. So horizontal, again, deal with the degree of the numerator versus the degree of the denominator. So we've got x squared on the top, and we have, x on the top and x squared plus 1 on the bottom. That means the degree of the numerator is 1 because x is the first, and the degree of the denominator is 2. So again, that gives us a y equals 0 for our horizontal, which is kind of nice. Ooh, drawing lines shouldn't be there. All right, we can still look for our x-intercepts because that's just setting the numerator to 0. So we take 3x, 5x, and set it equal to 0, which gives us that x equals 0, which gives us 0, 0 as our x-intercept. Because again, the y-coordinate of the x-intercept will always be 0, and we just found that x is also 0. Now, if we have 0, 0, then this guy is already done as well. Okay, so we jump to our x and y chart. But here's where it kind of gets a little bit tricky, because normally we use the vertical asymptote to tell us what values of x to pick. Without that, we're kind of on our own. So definitely use the one we already have, right? We know 0, 0 is a point. Which does look like it conflicts, by the way, with the y equals 0 horizontal asymptote. So this is going to be one of those times when we're going to cross the horizontal asymptote. It's kind of interesting. It's going to happen. So because we really don't have any place to sort of start, or any place that's going to be distinctly where we should be looking, kind of go around 0. So maybe we do, -1 and +1, and maybe -5 and +5, just to get an idea of what's happening near the middle and then sort of further out. You could go -10, +10, things like that. I was looking for ones that I think could fit on the graph that I've drawn so far. So let's see what we get. All right. If we plug them in, let's plug in 1 first, let's say. -5 first. So let's do y equals 5 times -5 over -5 squared plus 1. Well, 5 times negative 5 is negative 25, and negative 5 squared is 25, plus 1 is 26. So this, looking kind of like a huge number, is really just a little less than negative 1. So negative 25, 26. All right, that's interesting. So now let's see if we try plugging in our negative 1. All right, well, our 5 times negative 1 is negative 5, and negative 1 squared plus 1 is going to be 2. So this is going to be negative 5 halves, which is also negative 2.5. So either way you want to write it, that is fine. The next number we'll plug in is that positive one. I was trying to erase a little bit too small, I wasn't going to do it. So we get 5 times 1 over 1 squared plus 1. So we get 5 over 2. So we get positive 2/5 for this one. Oh, by the way, you do not have to pick symmetric points that I've picked. You are welcome to, but I'm just choosing them sort of at random. So if it seems like it's working out for me because I'm getting matching points so far, so I'm hopeful that I might get another set of matching points for the 5s. It doesn't mean that'll happen every time. Plug in regular positive 5 and we get 5 squared plus 1. So again, we're going to get 25 over 26. In this case, it's going to be positive though. Okay, so let's see if we can get an idea of this graph just from those 5 points. If we can't, we can always go back and get more. So put in your your horizontal asymptote first, and let's plot our points. 0, 0. So we're already violating our asymptote. 1 and 2.5. Negative 1 and negative 2.5. And 5 and just under 1. 1, 2, 3, 4, 5. Just about there. And negative 5. 1, 2, 3, 5. And again, just under negative 1. So I can start to sort of draw what I think the picture might look like and use the horizontal asymptote sort of to finish off what I think it will be. If that doesn't make sense to you, or if this graph isn't what you thought it was going to be, then you certainly can pick more points a little bit farther out to get a better picture. But I'm betting this is the graph, because the horizontal asymptote serves some purpose. So in our case, I think what it's going to do is it's going to hold our graph tight to it at the ends of the graph. It's going to hold the end behavior to it. The middle, we just have that one place that crosses it. Okay, so here you have 3 more examples of different graphs that you might see when graphing rational functions. Please feel free to email me or see me with questions. We will be going over any questions that you do have on Monday, going through a few more examples with this, and starting to review for a test in Chapter 9. Excellent. Thank you so much for watching. Bye-bye.